Okay, so our next topic after the Blasius form of equation. So you know that according to the Blasius form of equations or Blasius solution, the exact solution, we have the expression for the delta, that is the displacement thickness. We have the boundary layer thickness. We have the momentum thickness. We also have the wall shear stress. We have the frictional coefficients. So we all the things, all the parameters, we will also have different expressions when we solve this von Karman integral. Okay, so we have this equation. Von Karman is another mathematician. He tried to solve this problem for the real fluid. Okay, a little bit different way because his equation contains integration, so that's why we call this von Karman integral equation. And when we solve this problem, we will get another form of expression for wall stress, for momentum thickness, for boundary layer thickness, also for the displacement thickness, and also you can derive it for energy thickness. Okay, so we have two different forms. One is Blasius form, and another one is von Karman integral form. Okay, so before going to that, again we have some simple thing that you need to know, that there are some assumptions. Okay, so here we assume that the pressure is constant throughout the flow field of a flat plate. Okay, so remember that for the Blasius form of solution or von Karman integral, we actually consider flow over a flat plate. It means your plate is stationary and flow is moving in this way with u stream, u infinity, or you can say that us, that is undisturbed flow. Okay, so it means that the pressure is constant throughout the flow field of the flat plate. So over the flat plate, there is pressure is constant. Pressure, it will not change. Okay, this is your one assumption. It means anywhere you go, the pressure will be constant. And another thing, they said that the flow entering the control volume, okay, at the leading edge of the plate is uniform. So we will consider one control volume. Your control volume in this case is like this: A, B, C, and D. This is your control volume. Okay, so this is a flat plate. This is the x direction, this is y directions, and it said that when we have the beginning, or the flow is entering to the control volume at the leading edge of the flat plate is uniform. It means that, so flow is entering in this way, in this direction. So this is the leading edge and this is the starting of the control volume. Okay, so in this case, along the phase AB, all the velocity are u infinity. It's undisturbed flow and the flow is uniform. Okay, so this one is the second thing. And while the velocity of the flow exceeding the control volume varies from the upstream velocity at the edge of the boundary layer to the zero velocity of the plate, on the plate. So again, I'm saying, while the velocity of the flow exceeding, okay, exiting the control volume varies from the upstream velocity at the leading edge of the boundary layer to the zero velocity on the plate. It means that after that it has a uniform, but when it's flowing or leaving the control volume, the velocity will be starting from here at the leading edge, means upper one, that is equal to the upstream velocity, and it will continue to decrease until the zero at the plate or on the plate. Okay, it means the velocity profile will change from us, I mean the free stream velocity, to gradually decrease, and it will become zero if you move in this direction. So this is the leading edge or the upper edge of the control volume, and this is the lower edge. So lower edge, at the lower surface you can say there is zero, and upper surface you will have the us, I mean the free stream velocity. Okay, so it means that it actually follow the velocity profile is like boundary layer thickness, something like that. Okay, and the fluid adjacent to the plate makes up the lower portion of the control volume. It means that the lower portion of the control volume, it means the lower part is actually the plate itself. Okay, so we have the control volume, and for the control volume, the lower part or the lower surface is actually nothing but the plate itself, and the upper surface just coincide with the streamline outside the edge of the boundary at the exit. It means the upper control volume layer, the upper surface of the control volume, is just you consider outside the boundary layer. It means you can consider almost close to the boundary layer. It means that along the edge, your velocity is actually free stream velocity. We have 99%, yes, right, but for simplicity we consider along the edge the velocities are all us, right? And along the lower surface all the velocity are 0. Okay, that's clear. So that is our control volume A, B, C, D, and the flow is entering from where? A, B and B, C. Not only A, B, flow is also entering in this way. Is actually parallel, okay, not like angular form. So we will have AB and BC is inlet, and outlet is only CD, because AD is actually the plate itself, right? So here we also consider the flow is incompressible and a unit width. It means we are only considering two-dimensional case, and your x is in this way, but y in this case the width is 0, sorry, not 0, 1. And the pressure gradient, there will be no change in the pressure gradient. It means the gradient of pressure is 0. It means del P by del X and del P by del Y both are 0. Okay. So these are the definition of the problem. Okay. So in simple, we don't have any velocity gradient. Sorry, we don't have any pressure gradient, and we will have the flow is upstream. It means that just starting from the when the flow is entering to the control volume is all are uniform. The lower surface formed by the plate itself, and the upper surface is just considered outside the boundary layer. And we will have the flow inlet is AB and BC, and outlet is CD, because AD is actually the plate itself. We cannot have the in and out there. It's a wall. Okay, so based on the continuity equation, so what we will get now. So based on the continuity, so we have the BC. So it means that in this case, in is equal to out, right? So m dot BC plus m dot in is equal to m dot out. Okay, so here it means that if you go to the control volume, so in is here, this one is in, this one plus so this one in, I use a different color. This one in, this one is in, and this one is out. So it means that rate of change m dot AB plus m dot BC should be equal to m dot DC or CD. Okay, so in this case, so BC will be out minus in. So as I said, so here the resultant change is actually this one is nothing but this one. Okay, so we will find it out later on in the next slide how we are going to do it. So del by del x, in this case rho u dy dx. Okay, so how to get this one we will see in the next slide. Hold on 1 minute. Okay, so what is the Newton's second law? So you know that the force is equal to rate of change of momentum. So momentum out is equal to momentum minus in minus BC. Same like as I said, that out will be this. There is 2 in, 1 out. So out should be in, that is momentum for AB, and minus momentum of BC. Rate of change of momentum. Okay, that is the force. Newton's second laws motion. This should be Newton's third law. I don't know why they put this second law. Second law is SF equal to MA, and Newton's third law is rate of change of momentum is equal to force. Okay, it should be third law. Okay, I think the lecturer put second law, or I don't know why they put. It should be in third law. Second law is F is equal to MA. Okay, so next thing is we want to find out how we are going to get the expression, okay, for in and out, okay, resultant expression. So in this case, one moment, don't have enough time. So we consider the a portion of the control volume. Here the thickness is delta. Here the thickness is delta plus the d delta, okay, increase. The distance is dx. You understand what I mean? And in this case, when the flow is uniform, right? So when we consider the inclined entry, that is BC, here the stream velocity is US or U infinity, the flow field velocity. And So we consider the rate of change of mass first, then we relate with the momentum later on. Okay. So here you can see this m in will be rho v. This is rho a v. So in this case it should be rho, and this one is the velocity is u, and you need to integrate along the y direction. Okay. So 0 to delta, it means you need to integrate from here to here to here. That is the boundary layer thickness. Okay. That is rho u dy. So you know that q, hold on. Okay, so you know that q is equal to av, right? And you also know that m is equal to rho, this is volume. Sometimes we misunderstood with volume and the velocity. This is velocity. So your m dot will be rho into volume dot. Okay, so volume dot means volume dot is nothing but the flow rate, that is q. So we will have rho a v. This is velocity. Okay, so that's why we use rho. Area in this case it should be cross sectional area, that is dy, but the width is 1, so that's why we have 1, and you integrate the dy from 0 to delta. Okay, and next we have the m out. M out will be m in using the Taylor expansion, then del m by del x dx. This is the Taylor expansion. How, if you know the initial condition, how much will be how much rate will be after the distance of dx. So we can use the Taylor expansion, neglecting the higher order term. So initial condition, it means the when you have the x is equal to 0, in this case f in m in plus del m by del x dx. So it means that in this case you will have out will be, this is del m in, you already know, and then del by del x of del bc. Okay, so it means that you just need to differentiate the same property here, and then you have dx. So your out will be this much. Okay, so what will be your bc here? So this should be out minus in. If you put out minus in, so it means that I will end it here. Okay, so it means that this plus this, then minus of this, so this will cut down. Okay, and you will have only this part, you will have only this one. So that is the flow out, that is BC in this case. So out minus in, that's why we have this expression. Okay, from there. Okay, so that's why I would like to end here, so then I will continue.